In the previous two videos, we learned how to unit test a simple .NET class using xUnit, and then we looked at how to do some test-driven development instead of just cramming it all in at the end. So now we're feeling good. We have our class, it's 100% unit tested. It is a beautiful day. Unfortunately, our wonderfully unit tested code, well, yeah, it may have lots of tests, but the design of the code is trash. It is garbage. When I gave this similar talk to my team, I saw a lot of rather surprised faces. The code certainly didn't look awful. Maybe there were a couple of little things that they would have done differently, but it probably would have passed code review. And that right there is the problem. Little design decisions early on can cascade into much bigger problems down the road. If you don't recognize it, your code base is going to get more and more difficult to write tests for. For this talk, we're going to focus on identifying things at the design level that will make your current code and hopefully future code as testable as possible. Now, most developers are at least vaguely aware of solid design. So this is a set of design principles whose names match the letters of the word solid. But what I've seen is, with many of our well-intentioned developers, putting the principles into practice seems to stop being a priority once they exit the classroom. So briefly, here are the 5 principles. So we have single responsibility. Functions, classes, even source files themselves, they should capture a single purpose. Classes and functions that do less work and are more focused on a singular piece of functionality are easier to test. Moreover, they're also much easier to read and understand by the other developers. We've all seen the 400-line behemoth of a function that no one ever bothered to refactor, and then special case after corner case has to get hacked into it until that code was so tangled it could never be undone. Open-close principle. Software should be open to extension but closed to changes. A simple application of this is extending classes or implementing interfaces. The main point is you want to avoid the problem of a change somewhere requiring you to adapt that change in a bunch of other places. And this is a very common occurrence. For instance, you decide to make a parameter change in a function, and then all of a sudden all of your unit tests stop building. Liskov substitution. Objects of a superclass should be replaceable by any subclass, and your code should still behave correctly. Alternatively, any implementation of an interface should be equally correct for the code that operates on the interface. So oftentimes when your code starts requiring you to do a bunch of ISA checks to see if it's an instance of a particular subclass or if you're downcasting things, that's probably a sign that you're violating this particular principle. Interface segregation. This really is just simply break your interfaces and APIs down so clients and the implementers only need to concern themselves with the methods that are of concern to them. We've all seen code where half of the functions of a particular interface were left throwing a not implemented exception. Well, the problem could have just been a poor choice of which interface to use, but often the case is that the interface is so polluted with things that are only of interest to a very small subset of possible implementations, and they should be broken down into those smaller implementations, or smaller interfaces. So the last one, and I apologize, this is a horribly obtuse name, is dependency inversion. The spirit of it is that high-level modules should depend on abstractions and that the low-level modules depend on the same abstractions. Depending on concrete classes makes it much harder to test because your tests then depend on those other bits working. Now I want to stress that dependency inversion does not mean something like subclasses having references to their parents or something like that. No. It has everything to do with this idea of dealing with interfaces. Now, the two design principles that we're going to be focused on most are going to be the 2 orange ones, the first and the last one. It's not that the other ones aren't important, and I actually will mention them as we're going along. I'm just going to focus my attention on the first 2 because those are the biggest ones that are going to impact what we're doing for testing purposes. So the first theme of solid design was to focus on encapsulating things better. So let's take a look at what we're doing in that. So functions and classes should start capturing a single purpose. So let's take a look at a slightly better rewrite of this that's going to give us what we're looking for. So you can imagine, one thing might be the currency. So before we had this currency, it was sitting inside the currency converter class. Well, now I've moved it into its own separate file. And this is for the reason that if someone was going to look for our currency type, they were mandated to start looking through our converter code just to find out how a currency was implemented or which ones were supported. Now, this one can sometimes be a little controversial for some languages. A whole file for an enum? Are you crazy? But over time, I have stopped trying to get cute economizing my source files. The build times are generally not going to be impacted by this, and it's nice when you can look at a single file and know everything you need to know about it. You do not need to maintain monolithic files. So the next thing that we have in our code is a lot of primitive obsession. So this is a case of where your code is going to be littered around with lots of things like primitives like ints and lists and vectors and whatever they happen to be, but you're littering those all throughout your code, and you can't distinguish one int from another int or one vector from another vector. So let's review the old signature for convert currency. So if we look at it, we saw that okay, we're going to take one currency, and then we're going to take two currencies and a decimal, and we're going to give back a decimal, and this decimal corresponded to this currency, and we have to translate it to that to give us that. And then the poor soul who ends up using our convert currency has to reintegrate the decimal we gave back so they can match it up with their currency, and disembodied numbers and types are harder to work with. It makes the method signatures, they get bloated, and it's just harder to keep track of all of it. And as I said before, how do you distinguish one decimal from another? Search through all your code for all the decimals, and you're going to get maybe 10,000 hits. Well, let's stop and think about what we're trying to do, at least in this particular case. Well, what are we trying to represent? Money. Well, let me ask you, how much money do you have in your bank account? 300. 300 what? 300 US dollars. Ah, I know what that's worth. That's actually worth something. I have 300 Ingram bucks. Not worth the paper it's written on. So let's associate the two things together to capture what the money type is so we don't separate the two things that are clearly and obviously connected together. So this is the way that we should have written it. We should have created a money type. So we can see that it encapsulates having both the decimal and the currency together. As well, we can end up seeing that, oh, they're read-only types. I've made it a read-only value struct that we have here. And now we can start doing some nice things like being able to print out what the money is. Later on, you can decide to start doing something along the lines of, oh, hey, I need my money to make sure that we don't have fractions of a penny. Like, remember the problem from the first video? Well, someone can come along and make it so that this class or something that extends this class, they can implement a cold, hard cash money type. And then instead of having all the disembodied primitives everywhere and making it so you got to put that functionality inside of the classes that use it, well, no, now you move this out to the place where it belongs. You encapsulate it inside of the objects themselves. Well, now we can go and we can fix up the currency converter to be able to work off of that. So if we look at the function that we have here, we can see that, oops, let's go here. I got the wrong one there. All right. So we can see that it ends up taking a source money and a currency type, or we're going to pass in a money and a currency type. And then what we're going to return back is going to be a money that's going to be presumably of the same type, already in that target currency. Now, unfortunately, since I've changed the I've changed the, well, not the interface, but I've changed the method signature, I violated the open-closed principle. So now that's going to force a lot of our test code to have to be rewritten, right? So if I go back to the unit test code, where are we here? We go to, yeah, so now we can see, now I've got to pass in a new money type, and that's going to be passed in here. And unfortunately, yeah, all those tests are going to break until I do this. And this is why it pays to get this type of thing sorted out ahead of time and early on in the design phase, instead of trying to do it at the end or much later on. Because now we have to rewrite all of our tests, and that can introduce bugs. So remember in the TDD talk when I said that you have to get a failed test first before you start to write the implementation? Well, we don't get to do that now. So if I rewrite the test code properly and run my tests, I'm going to see all green lights. Now, are they all green lights because I wrote the test correctly, Or have I accidentally done something that's going to make it so that the test always passes and I actually am letting some bugs through? So you can see why, as time goes on, it gets harder and more risky to start to do these types of changes, because you're going to have to change a much wider set of potential code units in order to get this fixed. And with tight release schedules as they are, your team's appetite may not be to allow these types of changes to occur. And again, the longer you wait on this, then the harder it does become. So now let's take a look at one other aspect of single responsibility. And this is actually the bigger issue of the two. Again, it's nice that we've got money encapsulated. It's nice that we've got our currency moved out into its own file. But let's go back to that original code again. And you can see that we had this dictionary that was maintaining the USD conversions. All right, we got some primitive obsession there, I guess. We go down, we can take a look at, we had to load the USD conversion rates. We had the function that was going to create the static conversion rates. We had our function to allow us to look things up in the dictionary. And what have we done here? This code has nothing to do with currency conversion per se. But what we've actually done is we've adopted the responsibility of being an exchange rate provider. And I want you to think about that. The currency converter is supposed to have an exchange rate provider. Well, it doesn't. It's doing all the work, and it is a provider itself. So we've actually inflated the responsibility of this class in direct violation of the single responsibility principle. So later on, someone's going to go looking for something that does exchange rates. And sure enough, they're going to find this code and see that it's hidden behind a couple of private methods. And the next thing you know, they're going to be going, oh, I should just make these things public. Oh, great. Okay, I'm going to update the interface there. Well, now we're violating both open and close principle and violating interface segregation principle. And then a year from now, someone's going to be wondering why some class of theirs that doesn't have anything to do with currencies has this weird dependency on a currency converter, and they have this member called currency converter sitting inside their class. And at that point, the design has well and truly gone off the rails. So what we should be doing is factoring out the code into a class whose responsibility is to just do exchange rate provision. And then we can put the has a relationship back into our code. So let's again take a look at the new code the way it should be written. So now I have a USD exchange rate provider. So this is going to be the code. This is virtually the same as what we had there. Inside of it can have a dictionary. And we take a look. Yes, it's loading the table. And yes, we see it's got the same load rate as before. And all we've done is we've exposed this one single public method that's, hey, can you get the exchange rate for me? Ever so slightly different from what I did before. It threw last time. I'm just going to have it return either a null if it's not there, or it's going to return the decimal if it is. And then we can leave it up to the caller to decide how they want to deal with that. They can decide if they themselves want to throw an exception or not. So later on, someone may say, you know, I actually don't want to have a dictionary there. I want to do something different with it. Or I want to create my own exchange rate dictionary that very specifically will encapsulate, yes, I deal with currency to decimal. And more importantly, this has all been moved into its own location. So now if we go back to our code, now we have a USD exchange rate provider instead of the dictionary, and we're going to go ahead and we're going to instantiate that inside of our constructor. Now, we could take this even further, again, for primitive obsession. Notice I have the decimal that we have there. That's still yet another form of primitive obsession. Yep, can you do things like have a negative commission rate? Well, no, you can't. So probably we should be encapsulating a commission rate as its own type as well. And again, you can now see how this is supposed to be working. So for the purpose of this talk, I'm going to stop with what was done here. But again, once you start seeing it, it becomes very obvious in the code that you have. All right, so now we've done the S portion of solid. It's time to move on to the D portion, dependency inversion. And this is the payoff slide. And this is the more serious part of the refactoring for what we need to do. Now, the first thing you should be saying is, hold on a second. You refactored out some new code in that to make that exchange rate provider. Shouldn't you unit test that? Well, the answer to that is yes and no. Yes, of course, all code should be tested. But no, because that code doesn't really need to exist, at least not where it is right now. And I want you to think about what that class does in its current form. That class is just providing fake data. So the real implementation in the final product that's going to be shipped needs a proper exchange rate provider that deals with live data. And that's a problem that I've sidestepped over since the very first video. And again, I promised that the real thing was going to be much more sophisticated. We're just doing this so we can demonstrate unit testing and so forth. So where is it? All right, where is that going to be? And the real question is, well, once you have it, how the heck are we still going to be able to test the stuff that we have? So we need to be able to migrate over to the real version, but the real version's not going to be able to scrape the value, or it's not going to provide the values I scraped last week. So now most of our tests are going to start failing. Oh boy, what are we going to do now? Okay, so do we just comment out our unit tests? Do we go, hey, look, I validated my code with the unit test. It's great. It works fine. So now we can trust, as long as nobody promises to touch this code, that's great. We're good. We're solid. Don't worry about it. Nope, that's probably not going to fly. We don't want our builds to fail. Oh boy. I've seen this one before. Okay, I've got it. We're going to pass a Boolean parameter isTest into the constructor. And then inside the constructor, we're going to instantiate the right one. If we're in test mode, then we're going to instantiate that fake one in our constructor. Otherwise, we're going to instantiate the real one. And then we're going to litter our code inside with lots of if is test then code. Don't do that. The problem is that our beautiful converter is still beholden on itself constructing an instance of a working provider. I want you to look right back at that. It's right there. Plain as day. New. Right there. There it is. We have a hard dependency in our code on a concrete implementation of something that does exchange rate provision. So that means that anyone who wants to use or test my class requires a working version of the USD exchange rate provider. Full stop. We have indirectly made them adopt a dependency on something private in our implementation, and that is bad. In the case of the real implementation, maybe someone's working on that 3 doors down, and they're not going to have their code ready for a month. Oh, I guess I can't test my currency converter until your stuff is done. Well, no, that's not acceptable. And that's just it. The currency converter should not be depending on any one particular exchange rate provider. It should be depending on an abstraction. And that's the heart of dependency inversion. Depend on abstractions. And what that really means for us is we want it to depend on an interface. So then at runtime, we simply defer to whatever the implementation is that's provided to us, and our code should work with any of them, at least assuming Liskov substitution is in effect there. So this is what gets down to this concept of dependency injection. And you've no doubt heard about it, and I can't take credit for the quote, but it's a $20 term for a 5-cent concept. It seems very, very complicated and magical, and someone says, oh, we're going to use dependency injection. All we're really saying is you define an interface and let the callers of our object decide which implementation they want us to use. And there are many, 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 many fancy ways to be able to do it. But at its root, it's just a cute way to be able to decide which implementation you want to use for an interface that your class depends on. Once you can design your code in a way that it depends on the interfaces, then dependency injection just comes out of that very naturally. So let's go ahead and do that. Let's make our code more solid, specifically by applying the dependency inversion principle. So first, we're going to have to extract an interface for the exchange rate provider. So remember there was only one public method? Well, here it is, get exchange rate. So that's it. We now have our interface iExchange rate provider. And now what we're going to have in our code is we're going to, instead of instantiating that directly and having a member variable of that type, we're going to have a member variable of iExchange rate provider. Further to that, in our constructor, we're going to take in an iExchange rate provider. So that's going to be passed to us by our callers. We're going to store that inside of here, and then down inside of our code, we're going to use our exchange rate provider and let it provide for us the values that we end up needing. And we are 100% agnostic to what it's doing. So now we go and look at the callers of our function. So if we go back into the test code that we have, you're going to notice I no longer have my own currency converter here because I don't need it. It's going to be provided for us. The static exchange rate provider now lives inside of the xUnit code. And it is exactly the same as the one that was in there before. All I did was I changed the name to static exchange rate provider, and I made sure that it implemented exchange rate provider, which it already trivially did. And then finally, when code wants to instantiate our currency converter, what they're going to pass in is they're going to pass in a particular implementation of the exchange rate provider. So, for instance, all the test code that we had before can now instantiate a new static exchange rate provider, and we can go ahead and pass that in as the second parameter. Maybe one of your tests later on has to deal very specifically with what's going to happen when you have an offline version where we can't actually get exchange rates back. This might be a very serious use case that you have to take care of. Well, someone's going to be able to then pass an exchange rate provider that is the offline exchange rate provider, which is going to be able to allow our code to be tested with that. And more importantly, our code is agnostic to whichever version gets passed into us. And then if you look at what the account classes are going to do, they're going to be the ones that are going to be passing in the real implementation of what exchange rate provider we want to be using. So remember when I said we didn't need to test the exchange rate provider code? Hopefully now you can see why. That code never belonged in the currency converter project to begin with. It was only test code anyways, and it should only live with the test code. Now, before I finish off here, I just want to point out one thing. I said we should be using interfaces everywhere, and I just now alluded to the fact that, we have an account, right? You mentioned the accounts have to use the currency converter. Shouldn't we be having an interface for the currency converter? And the answer to that is yes, absolutely, wholeheartedly, 100% we should be doing that. I should be going over here to this currency converter, and I should be refactoring and saying, I want an interface. Yep, I'm going to call it iCurrency Converter. Okay, there we go. Currency Converter now implements an iCurrency Converter, and oh, look at that. I already have my interface defined for me. So yes, it's trivial to be able to do it, so there's no excuse. Now, if we don't do all of this, then we can't scale our testing. So think, to test the account, you needed a working converter that needed a working exchange rate provider that's going to need a working, and so on and so on and so on. With dependency inversion, you only ever have one layer of interaction. And I can't stress this enough. This is actually the key achievement we've accomplished here. We now have unit tested the middle layer of a program. Right now, we do not have the real account class that is going to use us in the shippable software. We also don't have the real currency exchange monitor provider object. But we have successfully unit tested the layer that's going to sit in between the two of them. So each layer can easily be tested in isolation of the others because we've applied the dependency inversion principle and depend only on abstractions. So hopefully you can appreciate just how poor the original code was. Again, on its own, it was perfectly fine and it may have passed review, but really it was a liability in waiting. And worse, it was organized in a way that encouraged and made it tempting to go down paths that we want to avoid that are just going to compound the problem. So hopefully when you're writing your code or you're reviewing your peers' code, you can start to catch these types of problems in the code that's being written so you can stave this off. So now we have a much more solid design, and it seems like our testing journey is complete. But with our well-defined interfaces, we can now dramatically improve how we go about writing our unit tests by being able to leverage mocking and stubbing frameworks. And that's going to be the topic of the final video in the series.